Practical approaches to parts assembly have to address the need for high precision and low part tolerances, which is challenging especially in the face of process uncertainties. Closed-form analytical modeling of dynamical interaction is cumbersome and intractable for problems of practical relevance. Instead of a systematic treatment of uncertainty, state-of-the-art methods in industrial settings require vast engineering efforts and inflexible setups to eradicate sources of uncertainty. In order to tackle these problems, we formulate the task of parts assembly as a kinodynamic belief space planning problem for an underlying impedance-controlled robot. Here, x desired denotes the manipulator's reference trajectory. The propagation of the dynamics of our belief state and the compliant manipulator is conducted using multiple parallel instances of a rigid body simulation. The resulting robust trajectories can be executed on a real robot without the need of further post-processing. Our method obtains robust assembly strategies based on a goal region specification and the parts geometry data only. Compliance is achieved through simulated Cartesian impedance controllers, all sharing a common reference control input x desired. We employ a particle-based belief representation of the system state, allowing one to reflect prominent sources of uncertainty such as grasp or localization errors. We extend an expansive space tree planner to non-deterministic domains, where the planner input consists of an initial belief and a target region in belief space. An iterative improvement of our solution is achieved using the AOX meta algorithm. Shown here, the execution of a robust assembly trajectory in simulation. The planning result is capable of driving the entire particle cloud into a desired target state. What follows is an overlay of the same trajectory executed multiple times on a real robot with noise-prone state information. The application of mounting an electrical fuse onto a top-head rail aims to demonstrate the industrial relevance of our approach. The generated trajectories fulfill the task at hand even in the presence of considerable uncertainties and very low part tolerances. The overlaid executions of the planned trajectory on a real robot demonstrate the planner's ability to systematically overcome system uncertainties. The method presented computes robust assembly motions from geometrical data as input only. We demonstrate the effectiveness of our approach in thorough experiments both simulated and on real hardware.